Okay, we're going to do some more practice problems here. We got some gas law, some simple gas law problems. Again, you should try each of these before watching this video, and then you should be coming here if you need help or to check your final answer. So, a gas is confined in a container with a pressure of 361 torr and a volume of 7.0 liters. The pressure of the gas increases to 480 torr, and I put a little decimal in there because that was supposed to be 3 sig figs, and it's ambiguous otherwise. So if we're just looking at all of the units that we have a pressure, and that's 361 torr. We have a volume, and that's 7.0 liters. Then we have a second pressure, we call P2, that's 480 torr. And then what is the new volume, right? So we're asking about a second volume. So what's the next volume in liters? Now, the thing that I want to show you here is that rather than remembering all of the gas laws, oops, that should be a T, we can kind of use the ideal gas law sort of rearranged to figure out all of the simple gas laws. So you don't have to memorize all of them individually. So if we look at this problem and we look at my gas law here, right, there is no mention in this problem of moles, and there's no mention of temperature, meaning that those things are going to be staying the same, which means that if they're not changing, then they're not going to be changing anything in my equation. So if I erase those pieces, I am left with Boyle's law, and arranged correctly also. So now we just plug in 361 torr times 7.0 liters equals 480 torr times V2, which is what we're looking for. So 361 divided by 7, or sorry, 361 times 7 divided by 480 is 5.26458 liters because torr will cancel out. That's V2. Now we have 2 sig figs because my V1 there is only 2 sig figs. So this is going to be 5.3 liters. That's the final answer. All right, so moving on to number 2. Again, pause here if you haven't gotten this far yet. But we can also, again, do this, where we do P1 V1 over N1 T1 equals P2 V2 over N2 T2. And when we go through and we look at our problem, we'll write out, so highly pressurized gas in a small container has a pressure of 1,234 atmospheres and a volume of, that's V, 4.88 liters. The volume of the container is expanded to, so right, that's telling us this thing was done to it. So that's going to be V2, 785 liters. What is the new pressure of the gas? And we're given units for that new pressure, so this is P2, and that's going to be some number of ATMs, atmospheres. So again, we can look at all the numbers that we were given and what we weren't given. So we weren't given anything about moles. We weren't given anything about temperature. So I cross those out. And again, this ends up being a Boyle's law problem. But we're sort of deriving that from this sort of more combined equation. So this will be 1,234 ATMs times a volume of 4.88 liters equals P2, which is what we're looking for, times 785 liters. So that container gets a lot bigger. So 1,234 times 4.88 divided by 785. So this is 7.6712, whatever. That's already more than I needed. So now liters here, because I've got liters on the left, liters on the right. When I divide, those will cancel, and so this will just be atmospheres. And now we got to look and see, okay, what's my smallest number of sig figs? Looks like it's 3. So 7.67 ATM V2, that would be the final answer. All right, number 3. So I'm going to write this out again. So we got P1 V1 over N1 T1 equals P2 V2 over N2 T2. This will work for any simple gas law problem. So since I know these are all simple gas law problems, I'm writing them out right away. So we got a volume. So it's a volume of 7,185 milliliters. Contains 8.701 moles. So N, my number of moles, is 8.701. The volume of the gas expands to, so the volume expands to, it's a V2, 9,277 milliliters. And then what is the new amount of moles in the sample? N2. So another way that we know that this is a simple gas law problem is because, look, I have two volumes, and we're talking about a change in volume. Two different moles, and we're talking about a change in the number of moles. So when I look at my sort of overall gas law here, what don't we have? We don't have pressure, we don't have temperature. Right? We don't have an initial or a final temperature or pressure. So that means that we can erase those, leaving everything in place. And so it's going to be V1 over N1 equals V2 over N2. This is one that you might want to flip the equation. So if I go N1 over V1 equals N2 over V2, if I flip both sides, this is the same equation. The relationships are all the same, so we can flip it as long as we flip both sides. So N1 now is 8.701 divided by 7,185 milliliters. N2 is what we're looking for, and that's going to be divided by 9,277 milliliters. And you might want to take a stab here too at guessing, just like, okay, should my number of moles go up or my number of moles go down? Right? Our volume gets larger, so it'd be reasonable to assume that my volume should get larger also. So if we take 8.701 divided by 7,185, and then I multiply that number by 9,277, looks like 11. So N2 equals 11.2344 moles. But again, sig figs. So looking at all of these, 4, 4, 4, we should have 4 sig figs. So N2 equals 11.23 moles. And see, our number of moles did go up. Okay. Pause there if you want. Next problem. A container holds a gas with a volume of 73.9 milliliters, contains 1.44 moles. The amount of gas is reduced to 5.580 moles. What is the new volume of the gas in milliliters? So before maybe I even write out my complete thing, if you're on a test and you're not sure if this is going to be an ideal gas law problem or a simple gas law problem, we are talking about gases, so you should assume it's one or the other. I can write things down like my volume. So I've got a volume here, 73.9 milliliters, and a number of moles. That's 1.44 moles. The amount of gas is reduced to, so it would be an N2, 0.580 moles. It's not milliliters, moles. What is the new volume of the gas in milliliters? So we're looking for a new volume. So V2 equals how many milliliters? So again, if I write out this P1 V1 over N1 T1 equals P2 V2 over N2 T2, hopefully you're starting to see the pattern here, right? What units do I have? I have volume and I have moles, but I don't have pressure, I don't have temperature. So I'll erase those from this equation. And now I can write my V1. So here I'm not going to flip it because we're solving for V2, so V2 is already in the numerator, so we don't need to flip this. 73.9 milliliters over N1, so 1.44 moles equals V2 over 0.580 moles. So 73.9 divided by 1.44 times 0.580. So 29.765 milliliters equals V2. How many sig figs? Looks like 3. 29.8 milliliters equals V2. That'll be the new volume. All right, so let's keep going. So now a gas sample occupies a volume of 7.64 liters. So it's a volume at a temperature, temperatures now, 313 degrees Celsius. The temperature of the gas is reduced to, so that's a T2. What is the new volume of the gas? Okay, so we're looking for V2. And that's going to be in liters, so capital L. So we could do P1 V1 over N1 T1, P2 V2 over N2 T2, and then we look at our units. So I've got liters. We could look at these over here if you wrote out the variables for them. So V, right? So we have volume, temperature, volume, temperature. We don't have any moles, so I need to keep volume, and I need to keep temperature, and I can erase moles and pressure. Excuse me. All right, now there's something else that we have to remember when doing gas law problems when it comes to temperature. The temperature has to be in Kelvin. So we'll add 273.15 to these. That's a 2. So 313 plus 273.15, 586.15, and then 50 plus 273.15. I don't know why I'm doing this on my other calculator. Do 3.15. So now we've got those in Kelvin. And now I can just plug in all of my numbers. So 7.64 liters over 586.15 Kelvin equals V2 over 323.15 Kelvin. And solve for V2. So 7.64 divided by 586.15 times 323.15. So it's 4.212 liters equals V2. How many sig figs do we have? So it looks like when we added 273 to that, that becomes 4. This one stays 3. That's 3. So 3 sig figs. So final answer here will be 4.21 liters. All right. So next, a gas occupies a volume of 82.8 liters. The volume of 82.8 liters at a temperature of 37 Kelvin. Very cold. The temperature of the gases increases to 344 degrees C. So T2 equals 344 degrees C. What is the new volume of the gas in liters? So V2. So how many liters? All right, again, got to change Celsius into Kelvin, so add 273.15. So 344 plus 273.15. That's 617.15 Kelvin. That's a huge change in temperature. And again, we could do P1 V1 over N1 T1 equals P2V2 over N2T2. And again, we checked, see, okay, I've got volumes and I've got temperatures, but I don't have any pressure, I don't have any moles, I don't have P or N, so we can get rid of those. And we're looking for a volume again. So this will start at 82.8 liters divided by 37 equals V2 over 617.15 Kelvin. So 82.8 divided by 37 times 617.15. That's a big number. All right, so 1,381.0816 liters equals V2. Big number indeed. And then when we go and we look at our units here, or look at our sig figs, right, this is 2 sig figs. So basically anything else doesn't matter. 2 sig figs is our smallest. So that would be 1,400 liters, but we can't leave it like that because that's not 2 sig figs, that's ambiguous. So this has to be 1.4 times 10 to the 3 liters equals V2. Okay. So a gas has an initial pressure of 0.821 atmospheres, volume, we can write pressure, 0.82 atms, a volume of 7.07 liters, and a temperature of 199 Kelvin. The pressure increases, so we have another pressure, 8.39 atmospheres, and the temperature rises to 614 Kelvin. What is the new volume? So we're looking for V2, and it's going to bleed over here a little bit. All right, now you've got 3 different variables, but look at this. If I do P1 V1 over N1 T1 equals P2 V2 over N2 T2, if I take a look at it, I have pressure, volume, temperature, pressure, temperature, volume, different order, doesn't really matter. That means the only thing I don't have is number of moles. And so I erase number of moles, and that gives me the combined gas law. And now I can just plug my numbers in. 0.82 atm times 7.07 liters divided by 199 Kelvin equals 8.39 atm times V2, that's what we're looking for, and then divided by 614 Kelvin. So 0.82 times 7.07 divided by 199, multiply by 614 to get that over to the left, and divide by 8.39, 2.1. You can see over there we got 2.131, but we're going to have just 2 sig figs here because of the 0.82 atmospheres. So, oh no, what did I do? So this will be 2.1 liters. All right, last simple gas law problem. A gas is initially at a pressure of 159 atmospheres, excuse me. So pressure of 159 atm with a volume of 0.452 liters and a temperature of 994.8 Kelvin. The pressure decreases, so P2, right, pressure changes, that's what that's saying, 41.45 atmospheres. And the temperature drops, so P2, 253.0 Kelvin. What is the new volume of the gas in liters? What's the new volume? So what is V2 in liters? And again, P1 V1 over N1 T1 equals P2 V2 over N2 T2. So what's not being included? The number of moles. And so 159 atmospheres times 0.452 liters divided by 9,940, sorry, 994.8 Kelvin. And then 41.45 atmospheres times V2 is what we're looking for, divided by our T2, which is 253.0 Kelvin. So I didn't need to change any of those pressures because, or the temperatures, because they're already in Kelvin. All right, 159 times, whoops, 0.452 divided by 994.8 times 253 divided by 41.45, 0.44095 liters. And how many sig figs do we have? Looks like my smallest is 3 sig figs, so 0.441 liters equals V2. Okay. So you might have noticed that there was sort of a pattern to those ones before. But for this one, I think that I said the last one's the one. I think I meant to delete this one, but it's on here, so let's do it. A weather balloon has a volume of 30.00 liters at 0 degrees C. What will the balloon's volume be when the temperature is negative 67.1 degrees C? So let's see, we have a volume that's 30.00 liters. We have a temperature that's 0.00 degrees C. And then we have a new temperature, a T2, which is negative 67.1 degrees C. And we are looking for, right, it says, what will the balloon's volume be when the temperature is lower? So V2 is what we're looking for. And I'm going to assume liters because we're starting out, our other volume unit is in liters. Okay, so first thing we have to do is notice, oh, our temperature's in Celsius. So I need to add 273 to those. And that will give us Kelvin. So this one will be 273.15 Kelvin. Negative 67.1 plus 273.15 is 206.05 Kelvin. Now, what equation do we use? P1 V1 over N1 T1 equals P2 V2 over N2 T2. So let's look. What do we have? We have volume and we have temperature, so we can erase pressure. No, that's not what I meant to do. We can erase pressure, erase moles, pressure, moles. And there's our equation. So 30.00 liters divided by 273.15 Kelvin equals V2, which is what we're looking for, divided by 206.05 Kelvin. All right, so 30 divided by 273.15 times 206.05 gives us 22 point, how many sig figs do we have? This one actually is now 5 because this had 2 decimal places. I guess that 0 is not significant, but the ones after are. It's a little bit weird. This one, that would be 4, 4. So it looks like we have 4 sig figs. So 22.63 liters equals V2. All right, so now on to partial pressures. These ones are given as multiple choice problems. the concept here is that if I know what the total pressure is inside of a container, which usually is going to be atmospheric pressure, in a problem like this, it's going to be equal to whatever the atmospheric pressure is. So that pressure there, 860 torr, is going to be equal to the partial pressures of all the gases that are inside the jar or inside the container. So we have CO2, oxygen, and N2, and we might write this out formally as pressure total equals the partial pressure of CO2 plus the partial pressure of O2 plus the partial pressure of N2. So my total pressure is 860. We're given those in torr. The partial pressure of oxygen is 180. We're looking for the pressure of CO2. Let's write CO2. Oxygen is 180 torr plus nitrogen is 320 torr. Now we can just solve. So 180 plus, oops, wrote those on. 180 plus 320 equals 500. So now I subtract that 500 from both sides. 860 minus 500 equals 360. So pressure of CO2 equals 360 torr. So answer is D. And 11 is basically the same thing. We got the same three gases. Now they're in a balloon. Now my atmospheric pressure is different. So atmospheric pressure is going to be the total. So 760 torr. And then I'm going to have 365 torr. That's oxygen plus the nitrogen, which is 195 torr. N2. What's the pressure of CO2? So partial pressure of CO2 would be the last piece that has to equal 760. So maybe another way you could type this into your calculator is 760 minus 365 and then minus 195. So 200 torr equals partial pressure of CO2. And so looking at these multiple choice ones, bubble in C. All right. I hope that helps with simple gas laws, and I will catch you in the next one.